to refraction. Investigating refraction then. We can use a Perspex block and a ray box to investigate refraction. If we set up the ray box and we use a Perspex block, in order to do the experiment, the first thing that we should do is, holding the block steady with a pencil, draw around the edges of the Perspex block. If we then have a ray box, and again using the ruler to represent the ray of light, if we shine a ray of light into the block at an angle, we will find that as it travels through the block, it bends. So as it moves from the air into the Perspex, so as it goes across this air Perspex boundary, it bends. And again, we use a normal here to show this bending. So the normal, again, remind ourselves, is at 90 degrees to the surface. And this is our angle of incidence. Again, between the incident ray and the normal is angle of incidence. We find that as the light passes into the block, it bends towards the normal. And we draw again with a ruler and a pencil, putting an arrow on. And we can see this is the angle of refraction. And this angle is smaller than the angle of incidence when we travel from air into Perspex. Now when it travels into the block, it also then leaves the block. So we need to draw another normal, as close to perpendicular as I can manage here. We draw another normal, and the ray leaves the block. When it entered it, it bent towards the normal. As it leaves the Perspex and goes back into air, it bends away from the normal again. So we're going from Perspex to air this time, and it bends away from the normal. And it doesn't just bend away from the normal at a random degree. The ray emerging from the block should be parallel to the incident ray. So set your ruler on the incident ray and then slide it down without adjusting the angle. And this is the emergent ray. So these two rays should be at the same angle. You do need to remember that as it goes into an optically more dense or an optically denser medium, such as Perspex, it bends towards the normal. And as it goes from the Perspex to the air, which is optically less dense, it bends away from the normal. So that's investigating it practically. The first step was to draw around the Perspex block. Then we set up the ray box so that it was at an angle to the surface of the Perspex, and we found that the ray bent towards the normal as it entered the Perspex, and then as it left the Perspex and entered the air again, it bent away from the normal again. We also could be asked about a certain ray of light that comes into the block at 90 degrees. This is difficult to see because I've drawn some writing here on the right hand side, but I hope you can see this. This is a new ray coming in, and it meets the block at 90 degrees. And what happens in this case is that the ray is not refracted at all. It continues undeviated through the block. So if the angle of incidence, you could consider in this case to be 0 because it's coming in along the normal, it simply transfers through the block unhindered. So let's look at some of the terms that you have to learn then. Light bends as it moves from one medium to another. We call this refraction. When light enters a denser medium, it is refracted towards the normal, and when light enters a less dense medium, it is refracted away from the normal. So for example, coming into the glass block, because the glass block is optically more dense, it's refracted towards the normal, and then as it leaves it again, from a more dense into a less dense medium, such as air, then it bends away from the normal. This is also true of water. Whenever light enters water, it bends towards the normal, and when rays of light leave the water, they bend away from the normal. So, why does light bend? Well, when light hits a denser medium at an angle to the normal, the light bends towards the normal. And this is because part of the light ray meets the surface before another part of it. If you think of the width of a ray, then part of that light ray is meeting the surface first, and then the other parts are meeting it afterwards. So part of the light ray meets the surface first, and when it meets the surface, it slows down before the rest of the light ray, and this causes a change of direction. So the light ray is coming from a less dense into a more dense material or medium, and this causes it then to slow down because it finds it's more difficult to pass through it. So part of the light ray slows down first, the rest of it then follows, so this causes a change of direction. If the light enters a new medium along the normal, for example, then the angle of incidence is 0 degrees, then it does not bend because all of the light ray slows down at the same time, because it all meets the surface at the same time, so it slows down at the same time, and then as it leaves the glass block, it all speeds up at the same time. So in this case, there's no change of direction. But whenever the light ray hits it at an angle to the normal, then part of the light ray meets the surface first and slows down before the rest, which causes a change in direction of the light ray. This is very evident whenever we consider apparent depth. If we were to look at a stone in water, and the stone sitting on the bottom of the surface of the water, in the bottom of, say, for example, a river or a stream, the stone is sitting at the bottom, but the rays of the light leaving the stone come up, and as they leave the water, they bend away from the normal. So rays of light come up from the stone through the water. As they leave the water, they bend away from the normal and enter our eye. But our brain assumes that these rays of light have travelled in straight lines. So it assumes that the ray of light has come up in a straight line. It doesn't take account of the fact of this boundary and the bending or refraction of the ray. So it assumes, it forms an image of the stone at a place where it thinks the rays have come from, which is higher up. So our eye sees the image of the stone higher up, so it's not as deep as we think, or we think it's not as deep as it actually is. So stone is actually deeper than our brain assumes it to be, because it assumes the rays of light have come in a straight line, whereas they've actually been refracted at that boundary. And there's a reminder again of the normal. So every ray diagram that you draw in terms of reflection and refraction should have a normal drawn at the boundary.